Hello friends and welcome to the module 6 and the last module in this course, and we will be discussing the unsteady flow phenomena in this. So there are two broader categories of unsteady flow phenomena. One is a gradually varying and one is a rapidly varying. So we'll discuss both those categories in this module. So to begin with, our learning objectives will be to analyze the phenomena of unsteady flow and its possible occurrences where we can find unsteady flow. Then we'll derive the governing equations for the gradually varied unsteady flow, and then we'll analyze a very special case of a uniformly progressive wave. So that is what our learning objectives are. So to define with, the unsteady flow occurs in an open channel when your discharge or depth or both vary with time at a given cross section. So your unsteady flow are also called transients. So they are also called transients. So in pipe flow also the transient phenomena is very known to you. That is water hammer is a transient phenomena. So unsteady flow are called transients. This can happen due to some natural causes, some planned action or accidental happening. So natural causes can be landslides. So they can cause some unsteady flow phenomena. Some planned action, that is, you are releasing the water from a dam or reservoir through some human control. And accidental happening can be like a burst of a pipe, or there is a burst in hydropower plant, or there is a dam break scenario. So these can be some accidental happenings. So depending upon the curvature of the water surface, the transients are classified as a gradually varied unsteady flow and a rapidly varied unsteady flow. So these two kinds of unsteady flow are there. So the gradually varied unsteady flows, they are essentially the flows where there is a small water surface curvature. So thus we can assume the pressure distribution to be hydrostatic. While RVUF, there is an appreciable change in the water surface in very short distances. Now in GVUF, you include the friction analysis, while in RVUF, friction doesn't play an important role. Example of a GVUF is a flood flow. An example of RVUF is a formation and travel of a surge due to sudden closure of sluice gate. So in a canal or elsewhere, if you suddenly close the sluice gate, there can be a wave which is propagating backwards, and that could cause a surge. Now we will see which some field situations that give rise to transients. So the first one, that is depicting a heavy rainfall at unsteady rate. So if your rainfall is happening at an unsteady rate, then that could also lead to transients. Now, snow melt or ice jam. So what happens that there is a big mass of snow, and such that it is being blocked, and suddenly if it starts melting, or that so it becomes unstable. And once it is on the upstream side, it may have that, there is some water is also being stored due to that, and it suddenly starts melting, then it will kind of break the entire barrier, and then it will flow. So that is a highly unsteady flow. Okay, so avalanche also is a transient where, unsteadily, however, water is in solid form there, but still it is a form of water only. So that is also an unsteady phenomena. Then next one is flow operated by spillway gates. So here you have a human action, that you plan that how much discharge will be operated through the spillway, and that can be planned. So that is there. Then we have navigation locks. So navigation locks are essentially meant for in navigation channels where you want to you have big vessels like ships and all, they are crossing from one part to another. So some very famous navigation channels are the Panama Canal, the Suez Canal. So there you find this navigation logs. In European countries also, waterway navigation is more preferred compared to other parts of the world. In India also, you have a couple of waterways. That is, one is in Kerala, one is in Ganga River and Brahmaputra. But navigation logs are less practiced in India. So there also, where you have a navigation lock, you suddenly open the door to change the water level. So there also unsteady flow can happen. Also, if there is a sudden load increase in turbines in hydroelectric power plant, then also unsteady flow can happen or transient can happen. And the last one is a natural phenomena, that is the tides which happen in the estuaries or the tidal rivers that cause a surge. So this is usually called a bore and it is propagated upstream. So if your river comes from this end and from here the sea comes, so it propagates upstream in the direction of river, and this is called a tidal bore. So these are the locations where you observe transients. So today we'll be discussing about the gradually varied unsteady flow, and then in subsequent lectures we'll be discussing the rapidly varying unsteady flow as well. So a flood flow in a river is a typical example of GVUF. Now, what is the application that usually we have a problem in determining the modification that happens in a flood hydrograph? So what is a hydrograph? Hydrograph is a graphical representation of discharge versus time. So it is, in physical sense, it is the response of a catchment to given rainfall input. So that is a hydrograph. So in a river reach, you have two locations. So at location one, this is the hydrograph, and location two, this is the hydrograph. So if the same hydrograph travels, then you cannot control the flooding. So flood routing is a process wherein you try to control the flood hydrograph, and that is called a flood routing, so that you can minimize the flooding in the downstream areas. So in the next lecture, we'll be focusing on flood routing. There will be more discussing in detail. So this is a background to flood routing. So the continuity equation of unsteady flow. So the continuity equation is established by the law of conservation of mass. Okay, so in this we consider two channel sections having an infinitely small distance delta x, which are separated by that. So this elemental strip is dA, the area. So dA will be T into dy, so that will be dA, and this is your initial water surface, the solid line, and then water surface at after time dt, that is this dashed line. So there is an increase in the water surface, and that we can represent as dy, that is the change in the water surface. So if you want to find the rate of change, it will be del by del t, that is the rate of change in time dt. So with this understanding, the change in discharge occurs at a rate of del q by del x. So what is the change in discharge in length, and change in depth with respect to time, that is del y by del t. Now, if you consider a time frame, because this is unsteady flow, so everything will be measured with respect to time. So what discharge change happens through space in time delta t? So that is del q by del x is a change in discharge that happens in space dx, and that happens in time dt, because an unsteady flow will always be a non-uniform flow. So that is why the term dx and dt both comes. So due to change in discharge, there is a corresponding change in the channel storage, or you may call volume. So that is T, that is a top width, into dx in the distance dx, del y by del t. Okay, so this is the volume into time dt. So now, but T into del y is nothing but change in area del A. So it becomes dx into del A by del t into dt. Now, if the water is incompressible, the net change in discharge and volume should be zero, because it is conserved. Okay, mass is conserved. So rewriting this equation, so you have del q by del x into dx dt, that is the first term, and second term t dx del y by del t, and then rearranging this as dx into del a by del t, so that becomes zero because it is incompressible. So this is zero. So let us simplify this equation. So on simplifying this equation, this dx and dt terms, they cancel out, so you are left with del q by del x plus t del y by del t, this form, and this form is represented as del q by del x plus del a by del t, that is equal to 0. Now from the continuity equation, you know q is equal to av, so substituting q equal to av, and then modifying the equation, so you have del by del x of va and plus t del y by del t, that is equal to 0. So we'll be performing the differentials. So this is a partial differential. So a is constant del v by del x, v is constant del a by del x plus t del y by del t. So now what we do, we will divide this entire equation. So equation 4 will divide by t. So this becomes a by t. The rest part is same. This is v by t and this is t by t. Now what is a by t? It is hydraulic depth, capital D. And your del A is T into del Y. So your del A can be written as T into del Y. So T gets cancelled. So on simplifying your equation 4, it becomes D into del V by del X plus V into del Y by del X plus del Y by del T. So your velocity changes with distance, your depth changes with distance, and your depth changes with time. So this is the continuity equation for your unsteady flow. Okay, with this, if we consider a rectangular channel of infinite width, your equation 1 becomes del q by del x plus del y by del t, and that is equal to 0. Now, since it is an unsteady equation, we will also involve the equation of motion. So that is a dynamic equation of unsteady flow. So in this dynamic equation, we treat the flow in two dimensional for simplicity, and that additional element, that there's a variable for time element, will be used. So the time variable takes into account the velocity of flow, which we saw in the continuity equation, and it also brings the force due to acceleration, which produces the energy loss. So because there is energy loss due to acceleration, and that is what is being produced here. So force due to acceleration, that is del v by del t. So if you understand this diagram, so we have a channel datum, and then we have channel bed with slope s naught, water surface slope sw, energy slope sf. In addition, we have an acceleration line slope sa. So because your energy loss is due to two components, first is due to friction loss and second is due to your energy acceleration. So that is why these two components are there. So you have section 1, section 2. So ultimately we'll be applying energy equation at both the sections, and then we'll be comparing. So at section 1 your datum is g, at section 2 it is y, your depth is y, and this is your velocity head, that is the total energy. But at section 2, which is at distance dx apart, there is the change in the datum, that is z plus del dz, change in the depth y plus dy, change in the velocity head, that is alpha v square by 2g plus d alpha v square by 2g plus head loss. Now this total head loss component comprises of two components, is friction and acceleration loss. Okay, so let us determine the force due to acceleration, that is change in velocity over time, that is acceleration acting on a unit weight of water, that is w by g into del v by del t. So this is a general equation of force is equal to mass into acceleration. If you consider the change in slope to be very small, then we only consider the acceleration in x direction, and the y component can be neglected. So now work done by this force bit, that is equal to w by g del v by del t into dx, that is the distance between two channels. So the work done, that is equal to the energy lost due to acceleration. So we divide this equation by W, and the head loss due to acceleration is given by 1 by G del V by del T into dx. So that is the head loss due to acceleration. Now, the overall change in head in that small length dx, so that we will analyze. So if we treat that as exactly steady flow, and except that we have an additional acceleration component related, so we can assume that very small length the change is happening, that is a steady flow, but we include that acceleration change also. So total head is a component of total head loss due to friction due to acceleration. So friction is sf into dx, and acceleration you already derived earlier. So your slope of acceleration line will be given as 1 by g into del v by del t. So in the above figure, we just apply the energy principle at two sections. So this section 1 and section 2, we just apply the energy principle, and let us simplify it. So by the energy principle, the LHS we already discussed, and RHS we have this change in datum, depth, velocity head. This is head loss due to acceleration, and this is due to friction. So on simplifying, these get cancelled, okay, and whatever you are left with, so this goes on left hand side, so that is d of z plus y plus alpha v square by 2g, that is equal to minus sf dx minus 1 by g del v by del t into dx. The total head, change in total head, that is due to friction and due to acceleration. So this equation clearly demonstrates that head loss is comprising of two components, that is friction and acceleration. Now, in steady, gradually varied flow, the change in head depends only on friction, and there is eddy losses are negligible. So what we do, we divide the entire the in continuation of the previous context, we divide the entire equation 8 by dx, and then we have partial differential. So we have del by del x of z plus y plus sf plus del by del x of alpha v square by 2g plus 1 by g into del v by del t. So on simplifying, we have this del y by del x, then this becomes alpha v by g into del v by del x plus 1 by g del v by del t, this term. Now del z by del x and sf as it is. So this is the general dynamic equation for gradually varied unsteady flow. But if you consider a prismatic channel, for a prismatic channel, minus of del z by del x, that is s naught, that is a bed slope. So if we refine this equation, so it becomes this form where on the RHS we have s naught minus sf, and combining the continuity and dynamic equations for gradually varied unsteady flow, they are also known as the Saint-Venant equation. So they are the Saint-Venant equations. If we dissect equation 11, it can be represented in very nice form. So I'm writing is SF is equal to S naught minus del by del x into v square by 2g plus y minus 1 by g del v by del t. So if I consider only two terms where SF is equal to S naught, that is a essential condition for uniform flow, and there is no time derivative. So it is a steady uniform flow. If I consider these three terms, so I get del by del x, so that is a non-uniform flow. So it is a representation of steady non-uniform flow, that is a GVF. If I take all the terms, so I get a time derivative also, so that is an unsteady non-uniform GVF. So single equation represents all the three processes or the types of flow which we have discussed till now. So that is the beauty of this equation. Coming to the last topic, that is the uniformly progressing wave or the monoclinical rising wave. So there is a special case of unsteady flow which is possible in a prismatic channel, and that particular case is called a uniformly progressive flow. What happens in this flow, that it has a stable wave profile that doesn't change the shape as it moves down the channel. So we will see in the next diagram. So just I'll take you to that diagram. So this is the diagram where you can see, so this is the wave front which is being developed. So as it moves down the channel, it will translate. So it will not change the shape, but it will translate the same shape as it moves downstream. So it will be a translation motion. So essentially that wave feature is not changing as it moves downstream. So notably, if we see the uniformly progressive, that is why it is called a uniformly progressive wave. So the wavefront position, successive position of wavefront at different times are parallel, so they remain parallel. The velocity of wavefront, that is also called celerity, that is greater than the mean velocity of water at any section of the wave, and the wave configuration travels downstream with a constant velocity, but the mean velocity may vary from section to section as your hydraulic radius and the surface slope will change. So a particular case of this type of wave is called a monoclinical wave that consists of only one limb that joins the two different portions of the uniform flow water levels, that is upstream and downstream of it. So these two portions are joined and that particular wave is called a monoclinical wave. So with this we derive the differential equation of a monoclinical wave. So typical monoclinical wave can be approximated as a rising limb of a flood wave. So if you have this flood wave, so this is called the rising limb of the flood wave and that is a monoclinical wave. So your wavefront moves with the absolute velocity of Vw, so that is the velocity. So if an observer who moves along with the wave, so for him the wave appears to be stationary. Okay. Now this unsteady flow can be converted to a steady flow system by inducing an additional velocity of minus Vw. So your velocity is Vw in this direction. So by inducing an opposite direction velocity minus Vw, it can be converted to an equivalent steady flow system. Okay. So in this monoclinical rising wave, this is the upstream having a velocity v1, downstream velocity v2, and this is the wave front. So this is a time t and this is a time t plus delta t. So this is moving with the velocity vw and this is the distance traveled in that particular time. So in this figure, we can see that this is a monoclinical wave, same representation is there, and if you want to convert into steady flow you apply another negative Vw, so that converts the system into a steady flow. Okay, so during a time interval t, the distance traveled by wavefront is Vw into t. So when the wavefront passes over the channel, it takes in a steady discharge. So at the front, the discharge is Q naught is equal to Vw minus V1 into A1. Now, since your wave configuration is stable and there is a constant volume, so it leaves behind a steady discharge, that is Q naught is equal to Vw minus V2 into A2 on the upstream side. So this is on the downstream side and this is on the upstream side. Now what is Q naught? Q naught is the steady discharge which flows through the wavefront in the upstream direction. So it is a discharge flowing through the wavefront in the upstream direction and we call it as overrun. So let us equate these two values. So Q naught is Vw minus V1 into A1, that is equal to Vw minus V2 into A2, and on simplifying it you get Vw is equal to V1 A1 minus V2 A2 upon A1 minus A2. Now this V1 A1, that is nothing but Q1 and this is Q2. So we can modify this equation as Vw is equal to Q1 minus Q2 upon A1 minus A2, and this equation gives you the velocity of a monoclinical rising wave. So that is a wave velocity. Now in this in equation 2, in equation 13, if there is no initial flow, so there is no initial flow, so this term becomes 0, then your Vw, that will be equal to your V2. And if there is initial flow, your Vw will always be greater than either V1 or V2. So that is a condition. So this is true because your wave must move more rapidly than the other water particles if it has to make up the volume of the wave configuration at any time. So that is why this principle is fundamentally valid. Now, if you want to find the maximum velocity of wave indicated by Vwm, so you just differentiate dq by dA. Now what is dA? That is d into dy. So your Vm becomes 1 by t into dq by dy. Now this term dq by dy is a slope of the rating curve. So what is a rating curve? Rating curve, so if this is a discharge, this is y. So with the change in stage, what is the change in discharge, that is being noted here. And at any instant, if you take the slope of that, so that dq by dy will give you the slope of rating curve. So this is called the rating curve. That is same as the stage discharge curve. So it is also called as the rating curve. Now, if you consider a wide rectangular channel and you compute the discharge per unit weight using Manning's equation, then uh, you have Qn is equal to 1 by n y raised to 5 by 3 s naught raised to half. You have a wide rectangular channel, so your r becomes y. Just differentiating this equation, so you have 5 by 3 into 1 by n y raised to 2 by 3 s naught. Now what is this term? This term is velocity or normal velocity. So this equation and this term, that is the maximum velocity. So this is VWM into KW into VN. So this KW is a constant, that is called the ratio of maximum wave velocity to the water velocity in a prismatic channel. So for a wide rectangular channel, if you want to compute this ratio KW, that ratio will be 5 by 3. So for different channel sections, you can get this ratio. So for Manning's equation, you got this. Now, my question is, if you apply the Chase's equation to compute Kw for a wide rectangular channel, will the value will be same as 1.67 or it will be different? So that is what thing you should try. Another question is that what if I change the channel section to a triangular section having side slope 1 is to 1, then apply both Chase's and Manning's formula, will the Kw value be same or different, so that you can derive. Okay, coming back to the discussion. So now what we'll do, we'll consider an equivalent steady flow. So we are giving another velocity in the negative direction. So you have d by dt of Vw minus V into del by del x of Vw minus V dx by dt plus del by del t of Vw minus V, that is equal to 0. So here is a space derivative, here it is a time derivative. Now Vw equal to dx by dt. So this is Vw and it is constant. So on simplifying, you get del V by del t, that is equal to minus Vw into del V by del x. So on simplification, you yield this form of the equation. Now, since your V is equal to Vw minus Q naught by A, so that is from the earlier overrun and the wave velocity equation, we get that. So since your V is equal to Vw minus Q naught into A, so just differentiating it. So del V by del X becomes Q naught T upon A square into del Y by del X. So if we substitute this equation 18 into equation 11, so equation 11 is this. Your this equation. So let us substitute your equation 18 into equation 11 and you get del y by del x plus 1 by g v minus vw. So this is a change that is being made, del v by del x s naught minus sf. So if you just simplify this equation, okay, and you have to use all these forms. So your v is vw minus q naught by a, and then this becomes del v by del x becomes q naught by a square into del y by del x. So all these forms, if we substitute and simplify, your final form is del by del x is equal to s naught minus sf into upon 1 minus q0 square by t gaq. So this is a differential equation of a monoclinical rising wave. It is very much similar to your GVF equation. Only difference is this Q naught comes into picture. So that's all for the gradually varied unsteady flow. In the next lecture, we'll discuss the flood routing and then we'll discuss the rapidly varying unsteady flow. Thank you everyone. Have a nice day.